My name is Roy Anderson, and this is a presentation slash training for advanced spectrum analyzer usage. Spend a little bit of time talking about how to get help. Then we'll jump into defining what RF power is and how to measure it properly with a spectrum analyzer. And then I want to spend a little bit of time talking about what a spectrum analyzer, specifically a swept spectrum analyzer, is and how it works, and how the different measurements that you can make on it, power measurements that you can make specifically, are done. And then we'll talk a little bit about a swept versus an FFT analyzer, which actually the JD785B is both of those. It's two different spectrum analyzers in one. And then I want to spend some time talking about noise, and specifically or especially how it impacts your uplink receives. And then finally, we'll talk about some of the standard measurements you can make and path loss calculations and those kinds of things if you're hunting interference. All right, well, let's jump into the getting help piece. So in this slide set is a list of, the 800 number. You can send email, you can hit the website, but also I've listed here myself as well as the other application engineers that work on this product. And these are all mobile numbers too, so if you want to get a hold of somebody right away and want to call one of us, you're welcome to do that. Obviously, if I'm in a training session or on an airplane or whatever, I'm not going to be able to pick up the phone. So you can always go through the Go VIAVI number listed at the top, and they'll log the call and make sure you get a solution and all that stuff as well. So anyway, in addition to that, there's various places on our website you can go to get documents, but there's a link specifically, this www.updatemyunit.net, and that's where we put all of our latest firmware updates and documents and software revisions and all of that stuff. You essentially need to scroll down to the CellAdvisor product line, which is what the JD785B is part of, and go in there and you'll see all the different files that are pertinent to that instrument. So I'd encourage you to go in there and update your units. Usually the software is changing at least once a quarter. So check and make sure you've got the latest version of firmware, and then you also have access to manuals and software, and we're going to be talking a little bit about some of the software today, briefly, specifically JD Viewer. So jump to that website and bookmark the link. All right, well, let's talk about what RF power is. A spectrum analyzer basically is a fancy power meter. And really, to use it effectively, you have to understand how power is measured and really what power is. And it also helps a lot to understand what noise is and how it impacts the spectrum analyzer, as well as, or especially, your receivers that are out in operation. And one of the problems that you have today is, in most cases, people just throw around power numbers kind of like they're quantities. And power is really not a quantity, it's a rate. So it's a quantity in the sense that it's a quantity of a rate. So it doesn't help when you're trying to understand what power is when somebody says, 80 dB or 80 dBm or, whatever it is, and they never really give you all the information around that, because power numbers, you have to know certain things about the number to make any sense of it. So we'll talk about that. So this is just a sample of two signals that are changing in time, and they're at different frequencies. And you'll notice that the frequency in the blue, or the signal at the frequency that's blue, is at a lower frequency than the one that's red, right? You can see it's changing more at a higher rate than the one in blue, which makes total sense. So this is kind of a three-dimensional view of two signals changing in time, and as they change, if they change faster, they move up in frequency. So the one in red is changing faster, it would be at a higher frequency. Well, you can look at both of those views, either a signal in time or a signal in frequency, and in a spectrum analyzer they would show up like this slide. You can see the signal that's red is to the right, or at a higher frequency, the signal in blue, right? Makes sense, hopefully. If you were to look at those exact same signals on an oscilloscope, you'd see this. And actually, you'd see the composite, which would be the black signal. So the red and the blue add up as they go positive, and then when the red goes negative before the blue goes negative, it draws down the composite signal. And so you get an idea here of what the signal looks like as a composite. So that signal, the black line on the screen, is made up of two separate signals at two different frequencies. And as you know, your technologies, LTE or CDMA, that you transmit with or receive with, those are made up of many, many different frequencies, right? Lots of complex signals being generated from a base station. So that signal is not just contained in one frequency. Because of that, signal changing in time impacts where it sits in the analyzer, and because of the fact that power is a rate of energy transfer, it's not a quantity like gallons, it's more like gallons per minute. It's a rate. It's energy transformed or transferred from one system to another. So when you talk about power, you have to talk about power over time and or frequency. And if you look at these two graphs, you can see on the amplitude that's the chart on the left that's changing in time, you'll notice that if you look at just one period, in fact, if you look at just one half a period, the amount of power transferred would be the same over one half a period, a whole period, 2 periods, 5 periods. The rate's the same. The amount of power is the same in that signal. And so if you were to look at that in frequency, what you'd see on a spectrum analyzer would be just two spikes. And that power level would remain constant because it's really not changing. But you have to also keep in mind what bandwidth you're measuring the signals over, because this signal is made up of two different frequencies. And if you measure just one frequency, say the one on the left, that would be less power than if you measured both frequencies, right? A wider bandwidth. Hopefully that makes sense. So when you're discussing power, you really need to understand, well, what's the time period? What's the bandwidth? And especially, you need to understand the bandwidth on a spectrum analyzer. If you don't understand the bandwidth of an RF power level, you really don't understand the number. Let me just ask you guys a question. So how many of you guys have heard the term RSSI?
Most of the time. They always want the RSSI levels.
Yeah, well, so when somebody gives you an RSSI level, they might say, oh, RSSI is neg 90, right? Well,
Right.
I would assume that'd be neg 90 dBm. That number doesn't mean anything when you say just RSSI because it doesn't have a bandwidth tag to it. Now, you can probably assume when somebody says RSSI, they're talking about a channel bandwidth, and if you know that channel bandwidth, the number starts to have some meaning. But it's really important to understand bandwidths along with the power number because power changes based on the bandwidth of the measurement. And because a spectrum analyzer is a band-specific device, in other words, it's measuring power in specific bands, you really have to understand the bandwidth associated with any power number to make sense of it. It's common, for instance, in LTE for people to throw out numbers. You know, for instance, my receive level is too high. Well, what's too high? And they give you a number, and you say, okay, well, what bandwidth is that? And most of the time, they don't know. And if I can't associate that number with a bandwidth, I don't know if it's too high or too low, actually. So you really need to start trying to get your hands on the bandwidths associated with power numbers. And we'll talk more about that when we talk about the spectrum analyzer and how it measures power. But most often when you talk about power, it's usually in watts or it's in dBm. And here's a couple of formulas. These will allow you to convert back and forth from watts to dBm. And one thing in particular I want you to notice here is that, when you talk about power in dBm, it's a power level relative to a milliwatt. So if you were to take a power level, let's say 1 watt, and you were to insert it in this equation, 1 watt, you'll notice, gets divided by 0.001 or by a milliwatt. So that's relative to a watt. So even though power dBm is a log-based number, it's an absolute power number because it's relative to a milliwatt. Hopefully that makes sense. Here's just a simple table that I generated that shows you that if you have certain value in watts, you get a certain value in dBm just based on the formula. But there's a couple things from this table you'll notice. One of them is this. When a number changes in dBm times 10, okay, so if you go from for instance, so I don't know, you go to times 10 or divided by 10, in this case, you go down, you basically just shift the decimal place. So, yeah, go ahead. So the bottom line is a change in a linear scale from 1 to 10, right? If I go from 1 watt to 10 watts, that changes in dB plus or minus 10. Hopefully that makes sense. So you can, in your head, calculate fairly easily a change in power values of plus or minus 10 on the dB scale is actually a change of times 10 on the linear scale. The other thing that's really useful here is knowing that when you double something, like if I go in watts, if I double the power in watts, that's plus 3 dB in the dBm scale. Or if I cut the wattage in half, I go from, I don't know, let's say I go from 20 watts down to 10 watts, I reduce by 3 dB, right, in the dBm scale. And so that's useful. As we talk about the spectrum analyzer, you'll see places where that actually works out. Sometimes you wonder, if this math stuff actually works, but it does. When you talk about decibels, not dBm, but dB, that's a relative power number. In other words, it's, in my equation here, that'd be the power value 1 relative to power value 2. dB doesn't say anything about the absolute power. It just says, hey, it's higher or it's lower. It just tells you how P1 relates to power 1 relates to power 2. But dBm, because it's referenced to a milliwatt, is actually an absolute measurement. All right, well, let's talk about the analyzer specifically. So I said right at the beginning that a spectrum analyzer is nothing more than a fancy power meter. And all a swept spectrum analyzer does is it steps across the screen and measures sequentially power in little tiny bins or buckets, whatever you want to call it. And every time it sweeps and steps up, it measures another power value. And so literally what happens is it goes across the screen, it's measuring, and hopefully you can see this animation. It's measuring in steps the power level as it goes across. It then takes those power values and simply draws a line between them. That's all it's doing. It's just a fancy power meter. And all the measurements that you see on the screen are related to a bandwidth. The bandwidth on a spectrum analyzer is called RBW. That's the key measurement that determines how much power the analyzer sees, and that's what positions the line on the screen at a particular level, is how wide that bin is. So that's one of the key settings on a spectrum analyzer. So if you go from the far left of the display to the far right, that's the span, but within the span, RBW bins are where the power is being measured. And as you can imagine, as you lower the RBW, you know, for instance, I don't know what I have, how many bins I have, maybe 20 some on the screen here. If I were to double the number of bins, it's going to take twice as long to make the measurements across that span. So sweep time goes up as you lower the RBW. So here's an example of a screen, pulled this off the 785B. So every position on this line, that yellow line in the grid, every single position on that line, wherever you look at it, represents a power value in an RBW bin. So if you look on the display, the RBW on this particular screenshot was set to 10 kilohertz. And so when you look at that display, what it's telling me is how much power is in 10 kilohertz at any frequency within that span. So I just picked 2 points, 2 little peaks that were showing up there. And one of the peaks is at neg 90 dBm. The other one's at neg 75 dBm. Those particular peaks represent the amount of power in a 10 kilohertz bandwidth at that particular frequency. Does that make sense to all you guys, hopefully?
Yeah.
All right, well, one thing that happens when you look at that, when people look at a spectrum analyzer, they go, okay, well, there's noise and there's signal there, right? And you can see that. But those peaks or those values on that line don't represent the amount of power in the signal. They represent the amount of power in a 10 kilohertz slice of the signal. And so really the signals that you see on the screen that are above kind of that displayed average noise, they're made up of bunches of slices. So you can't really get the power in the signal because the bandwidth doesn't include the whole signal. Here's a couple of different examples. Maybe we got somebody who needs to mute again here. But here's 4 different examples of screenshots. The only thing that was changed, I just tuned to a broadcast channel that was down at 98 megahertz. The only thing that was really changed here was the RBW, and I want you to notice a couple of things. Starting at the top left, the RBW is set to 10 kilohertz right here. And you notice that the displayed average noise level is at about minus 110. Then I lowered the RBW and took another screenshot. This one is RBW at 3 kilohertz. And you'll notice now that the line has gotten lower. It's now at about neg 115. The next screenshot, I lowered it again. I went from 10 to 3. This one is at 1 kilohertz. And now the line is down at about neg 120. And again, I lowered it once more to 300 hertz. And now it's down around neg 125. So do you see what's happening with the line on the display? It's going down because those bins are getting narrower. And every time you narrow the measurement bin, the bandwidth, the power's lower because there's less signal in that smaller slice. So one thing that's interesting here that you'll also notice if you look is that the peaks on those transmitters, the signals themselves, they're dropping too because I'm now taking smaller slices of those. So lowering the RBW gives you more slices across the screen, and it causes the whole line to be shifted downward because the amount of power is less that's being measured in each little bin. One thing you'll also notice, just notice here I'm at a sweep speed of 47 milliseconds. And then as I decrease the RBW, it goes up to 194 milliseconds. So the sweep speed is also dropping because I'm lowering the RBW in swept mode. All right, so how does that impact making power measurements? Well, if you look at the line on the display, if it's made up of the amount of power in a little bin, if you need to measure the power of a whole signal, you have to either go in and add up all the little bins manually, or you can do what you normally would do on a spectrum analyzer, a modern one anyway, is make a channel power measurement. So if I had this swath, you can see this green area right here of my signal. If I wanted to measure the amount of power in that bandwidth, I could go in and I could move and measure every little tiny position where the line is at in 1 kilohertz. My RBW is set at 1 kilohertz. So I could add up all the 1 kilohertz slices that make up this display and add them together, and that will equal this channel power number down here. Oops. And you'll notice that that's significantly higher than even the peak of the signal is. One other thing too about this, notice that the marker, I've got a marker set at the peak in this signal, and you see how the marker level is neg 98? Or no, what is that? It's not 98. It's neg 88. So the marker on a spectrum analyzer also represents the amount of power in a single RBW bin. It's not the power in the signal. The signal is much wider than that RBW bin. So if you want to make a channel power measurement to measure the power in a signal, you would need to go to Mode, Spectrum Analyzer. And on the 785, once you're within the spectrum analyzer, there's a bunch of different measurements you can make. One of those is channel power, and you can hit the measure key, which is button number 1, and make a channel power measurement. And then if you want to change the width of this green swath that goes up and down the screen, which represents the bandwidth, like on mine, it's set to 500 kilohertz. then what you would need to do is go into the measurement setup for that particular measurement and change the integrated bandwidth to 500 kilohertz or whatever bandwidth you wanted. And then one last thing, if you are ever going to measure power on a spectrum analyzer, make sure you don't overload the front end. I generally try to make measurements at 0 dBm or lower. And I think all you guys, when you ended up with your units, you should have an attenuator included with that kit. And so if you have any doubt of the amount of power that's going in the port, put the attenuator on. And then you can use, press the amplitude scale key on the bottom and put in an external offset in that represents how much that attenuator is, because the instrument doesn't know about the attenuator. And for you to get an accurate number, you have to back that attenuator back out of the measurement. So amp scale external offset will compensate for an external attenuator. Okay, well, if you need to convert from a trace level versus the trace to a channel power level, then you can use this formula if you want to do that. Essentially, it just scales it up. So if I had 10 bins that I was trying to get the power level for, I could use the channel power measurement and have it do it for me, or I could do it this way with the formula, either way. All right, so all power measurements are bandwidth specific, and keep in mind that if you don't know the bandwidth, then you probably don't understand the actual implications of the power number that you're talking about. Okay, well, I said early on too that this analyzer was really two spectrum analyzers in one. It's a traditional swept analyzer, but it's also an FFT-based analyzer as well. An FFT-based analyzer doesn't do what we talked about before, where the analyzer steps across the span and makes measurements. It uses a completely different method, and because of that different method, it's much faster at very narrow RBW. So if you crank down the RBW to 1 kilohertz on a wide span, it's going to take a while to sweep. And if you're doing something like hunting for interference, it's just too slow to be usable. And so in this analyzer, if I switch over to FFT analysis, what it does is it captures the signal and digitizes it and then converts it from the time capture to the frequency. You can just do math and get the frequency output. And because of that, it's much faster, but there's some advantages and disadvantages of both. A swept analyzer is a little more accurate if you're trying to get good accurate measurements. It has good dynamic range, which means you can measure small signals in the presence of larger signals better than an FFT analyzer can. But the main advantage of an FFT analyzer is it's fast. So if you narrow the RBW way down and start slowing down, then you're going to want to put it into FFT-based mode. And to do that, you press the sweep key on the keypad, and then you press sweep mode and choose fast. And you'll notice up here in the top left now on this display it says FFT. And the sweep speed is down, it's 26 milliseconds, even at a very low 1 kilohertz RBW. So for most interference hunting applications, you're probably going to want to run in FFT mode. So sweep mode fast, sticks it in FFT mode, and off you go. Now, so if you're making measurements for receivers, receivers have a noise floor threshold, and it's all based on the communication technology's bandwidth. And again, as you measure the spectrum, the amount of noise that's in a particular bin, as we saw on those sample displays, gets lowered when you narrow the RBW because there's less bandwidth and less noise in that particular area. The advantage of lowering the RBW is that as you lower it, the noise in that bin becomes smaller and smaller. So signals that are present in the same bin start to pop out because the signal to noise ratio starts to come up. In other words, if the bin is wide enough, there's so much noise power that signals don't show. But as the bins get narrower, the noise goes down, but the signal is still there at the same level. And so now all of a sudden, the signal to noise ratio kicks in and you start to see these spikes show up that you didn't see before. So cranking down the RBW is almost essential to try and find interference because you're a long ways from the signal and it's down in the noise. You know, the term down in the, it's in the noise means it just doesn't see it because of the amount of power in the noise. So all the different technologies out there have a noise floor, and if you look at this chart, it turns out that in a 1 hertz bandwidth, there is 174 dBm of noise. It's always there. It can't get rid of it no matter what. It's always present. And so when you talk about different communication schemes, they operate in particular bandwidths. And so they have certain amounts of noise that are always present in those bandwidths. For an LTE base station, and by the way, LTE is a little bit different. Let's talk about CDMA first. CDMA, all the phones and the base stations communicate to each other within 1.25 megahertz channels. And if you do the calculations for the noise, that means that there's about neg 113 dBm of power in just the noise. So the receiver, looking out over the air, is always going to see at least that much noise over that bandwidth. LTE, on the other hand, it operates in a much narrower bandwidth, even though the carriers are wide. So you might have a 5 meg carrier, or a 10 meg carrier, or even a 20 meg carrier. It doesn't matter because LTE uses 180 kilohertz resource blocks to communicate inside of. Because its communication block is narrower, there's less noise. And so a radio can be more sensitive when it's looking at a resource block in that particular area of the carrier. It's looking at just that little slice. And so noise and interference is a bigger problem in LTE, in part because it's more sensitive. It's using narrower communication channels. A small little signal in that one little channel can screw up that little channel. Does that make sense to you guys, hopefully?
Yeah.
So that's the noise level. In reality, those theoretical noise levels are a little bit higher because your antenna, the feed line, and the radio all add a little bit of noise. And if I just, you know, pull a number out of my hat here and say that it's 3 dB, then the real actual operating noise floor of a CDMA base station is about neg 110. Of an LTE base station, a resource block's actual noise level is never going to be better than neg 118. That's as good as it'll ever get in real terms.
I got a question real quick before you move on. So
Yeah.
if so for us to actually zoom in or change our span to actually see the interference, how do we actually pinpoint that frequency so we know exactly, or then start trying to find it? How would you do that?
Well, let
So,
me give you a quick example. So I've got the analyzer up here and I'm running it, correct? And I'm going to switch just to the spectrum display. So right now my RBW is set to 1 kilohertz. I don't know if you can see that or not. But I'm going to raise that so you can actually begin to see what happens at a higher RBW level. Let me go up to 100 kilohertz. So you see how you can't really even tell if there's something there now?
right. Yeah, it just got more distorted, yeah.
Yeah, so what's happened, by widening the RBW, I'm taking in far more noise in the measurement relative to the amount of power that was in the signal. But now as I lower the RBW and my measurement bins get narrower, the signal is stronger relative to the noise because I'm measuring less noise. And so those signals begin to pop out of the noise. So when you're looking at a noise floor, you want to be at a very narrow RBW because you've got to be able to look down below. In fact, for LTE, you really have to see a ways below neg 118 in order to see the noise that might actually impact the receiver. And so one of the steps is to lower the RBW and look at your channel. And as you lower the RBW, those interfering signals are going to begin to pop out. Does that make sense? So trying to find them, now I can see where they're at. I can actually put a marker on the display and say, hey, go to the peak. And now the marker is going to end up at the peak of one of those signals, and it'll tell me what frequency that peak is at. And I can go down, hunt it down, and kill it, right?
All right. And we're going to be plugging this right into our antenna, right? I mean, we're going to look out through the antenna to find this interference, or should we just be?
Yeah, that's a good question. So one of the training sessions is on CIPRI, but actually, if you have ground-based base stations in your market that have receive ports, some do, some don't. The newer ones tend to not. But it used to be all base stations had receive ports, so you could jack in with a spectrum analyzer and actually look at what the receiver sees. Nowadays, the radios are all remote, right? You can't get to them.
Right. So we can use a remote through Bluetooth, right? We can we can actually connect to it. If,
well,
our tower guys are up there hooking into the receiver, we can technically see their display and we can actually control it from the ground. Is that true? Yeah.
Well, you could do that, but that's kind of the hard way to do it. You could actually connect to the optical port or through the fiber and look at the signals that are going back and forth on CIPRI, because the RF is actually in the CIPRI optical data. So you can actually see the RF via the optical, and you can get the same kind of a display. So, and if you, when you get a chance, look for some of the other training sessions that are coming along, and specifically RF over CIPRI, because you can see what the base station sees with CIPRI.
Okay.
Now, when you're out hunting for the interference, you've got an antenna hooked up to your analyzer, right? Then you're going to be driving around looking for the interferers somewhere in the environment.
Right. Okay.
Yeah.
Yeah. That's probably what our next step would be, was to alleviate, multiple power climbs and checking everything up there. I mean, once we check connectors and everything, we kind of have our hands tied once we are like, okay, it's external interference. Now, how do we find it?
Yeah, well, I would even before that, I would say you want to go go out there and look at the base station with CIPRI if you can't jack into it and determine, is it external or is it internal, because you can tell either one of those before you get a tower crew out there. So you don't encounter the expense.
I'm sorry, what is CIPRI?
CIPRI is the format of the data on the optical link, basically. It's just called the CIPRI link, CIPRI optical link.
Okay.
Yeah, so
yeah,
if you watch for those other trainings, because the CIPRI training will help a lot in understanding that. Which market are you in, by the way?
Erickson market, over in Tampa, Florida.
Oh, okay. So at some point, hopefully, you'll get a chance to either jump on one of the online ones, or somebody will be in your neighborhood and we'll do an in-person training.
Perfect. Thank you.
Okay, so one way to look at the base station is to look at the channel power that's at the base, in the base station. So for say a CDMA base station, how much power is actually in the channel? And so you can do a channel power measurement and set it and say, okay, that's how much power is in my channel. And you can do that with the RF port if you have a way to connect to the receiver with the RF port on the analyzer. If you don't, then your only option probably is going to be with CIPRI. Now, unfortunately, in CIPRI, you can't measure channel power because the radio digitizes the signal before it sends it down to the BBU. And so you can't do a channel power measurement because it's tweaked all the power levels. It's digitized it, basically.
Oh, it just hangs up.
So in that case, what you have to do, if you want to compare it, you want to look at a good sector and then compare it to the bad sector. If you need to make a channel power measurement, here are the steps. It's in the slide set on how to make a channel power measurement. I'm not going to bore you with every little step, but they're in the slides. If you want to monitor spectrum over time, then usually what I recommend people do is use the spectrogram feature. Now the spectrogram works on CIPRI or works on the RF port. You can use it on either mode of connecting and looking at the RF, and the display is very similar. You'd see very similar things. In here are the steps on how to set up the spectrogram for the RF port. And by the way, this is also the same set of steps you'd use to configure it when you drive, if you're looking for an interferer. If you turn on logging, if you're looking at spectrum, whether you're looking at spectrum for over the CIPRI port or spectrum over the RF port, you can log the data and it will save the data out to a file, and you can then open that file with one of our software tools called JD Viewer. And JD Viewer is a free application you can download from that link, updatemyunit.net, that I gave you early on. And you can play back all those spectrum traces. So what this thing is doing is it does a full sweep of the spectrum, and that comes up in the lower grid, right? It then color codes the value of each of the measurements it made, each RBW bin, and color codes it according to this chart over here on the left, and then spits out a line at the bottom of the display. And then it does another sweep and it pushes up the line. It keeps pushing up the line. And so what you see is over time, this might be a minute later at the top, and what's happening right now is at the bottom. And you can then save all that and log it and then just go through it in time. There's a slider. You can grab the slider and drag it across and, you know, crank through hours of spectrogram measurements looking for something. Or you can, you know, use it like a VCR, and you can change the playback speed and do all that kind of stuff. But that's really useful for monitoring kinds of purposes. Let's say I have a base station that gets hit at the middle of the night, and you're trying to capture the signal. Well, you don't want to sit out there at 3 in the morning. You could go in there before you go home in the evening and set the analyzer up and start logging to a memory stick, and then come back the next day and grab the stick and load it into your PC and just review all the data. The other thing you can do is if, say, you're interference hunting, you're driving along the road looking for an interferer, you can actually turn on this time cursor. It'll stop the measurement, and you can then move this position indicator that's right here, that little green arrow. You can move it back in time to capture the signal when it popped up. And again, that screen is most useful for interference hunting. So let's talk briefly about interference hunting. I have 5 rules that I try and live by when I interference hunt. First one is I want to see what the receiver sees. If I can't see what the receiver sees, or I can't see interference on the receiver, it's not interference. Because you can go out in a sector and find interference all day long, but if it never gets back to your receiver, it doesn't matter. You always want to use a passband filter for the uplink, because if you don't have a passband filter, you're going to drive by a base station and you're going to get hammered by its transmit. And when that happens, you go blind. The receiver goes blind, and it, you know, overloads it, and it resets all the settings. It really makes it painful to try and interference hunt. You really want to get your hands on passband filters if you're going to do interference hunting. Also, gain is critically important. DANL is critically important, and we'll talk more about that in a minute. And then also, you may want to figure out how to calculate path losses, and so I'll talk briefly on those. So when I drive, I typically have a mag mount antenna through a passband filter, and then I'm running the spectrogram. And the DANL, or that passband filter rather, prevents this thing from overloading. When an analyzer gets overloaded, it sprays out junk inside the analyzer. And that junk shows up on the screen as signals that look like they're real, but they're not. They're fake. They're just artifacts. Every analyzer in the world does this. Ours is pretty good at detecting overload, better than almost any portable I've ever used, but it's not perfect. So you're a lot better off with passband filters. One of my other rules is gain and DANL are important. Remember when we talked about the noise level, the display noise level on the spectrum analyzer? By narrowing the RBW down, it pushed down that noise floor. Well, every 6 dB you can push down that displayed average noise floor, doubles the distance at which you can see something. So if I'm hunting for interference, and if I have my DANL set at, let's say, when I'm right on top of it, you know, 10 feet away from it, I can see it when my displayed average noise in the analyzer is at neg 100. Well, if I can get it down to neg 106, that means I can see it from 20 feet. If I can get it down to neg 112, I can see it from 40 feet. If I get it down to, you know, to neg 118, I can see it from 80 feet. It's pretty easy on this analyzer to get the DANL, that displayed average noise level, down to below neg 130, which means you could see it from hundreds of feet away. And so that's how you have to, you know, you've got to crank down the RBW so that you get the thing super sensitive. Otherwise, you're going to be driving forever, and you may never see it. And just as a little tidbit, every time you crank down that displayed average noise level by 6 dB, you see something from, you know, twice as far away, but you decrease your driving by a factor of 4. So if I go from neg 100 all the way down to neg 135, my driving just went from 8 hours to 5 minutes, right? So everything you can to get good gain and low DANL. That means low loss cables. Make sure your cables are good. Turn the preamp on inside the analyzer. All those things are critically important. Again, here's another slide on DANL, but I think you guys have gotten the message. Here again, same kind of setup keys to set that spectrogram up, the one that I just showed you, the sample I showed you. All right, and then finally, path loss estimates. If you want to, and we don't have time to go through it in gory detail, but if you want to, you can use this slide to help you calculate path loss estimates back to the base station. Essentially, you're going to measure a power in the analyzer. The line will be at a certain level, right? So if you're looking at some interference with a directional antenna and pointing at it, you can see where the line is. You can estimate, okay, well, that line's at about neg 85 dBm. So that's the starting point on the analyzer. And then if I work my way back through the cable, I've got a dB of loss to the antenna. And then the antenna has some gain. So I get a little bit of gain. So it goes up to the antenna because I'd lost some. It's a little higher at the other end of the cable than it is at the analyzer. But the antenna has gain, so it's actually lower on the other end of the antenna. And then there's some loss over the air from the actual interferer to the antenna. That loss you can calculate using this little table that's in the next slide. And just pull the numbers out of it. So here, 10 meters at 850 is 51 dB. Let me go back. There's my 51 dB. That means that the interferer is about neg 37. Now, if I estimate that it's at neg 37 at the point of the interferer, then I have path loss over to my base station. I can, again, look up in that little chart, and it says my path loss is 91. That means it hits the base station antenna at neg 128. There's gain in that antenna, so down here on the other side of the antenna, it's neg 110. Then there's some loss in the cable. Finally, it hits the base station at neg 113. So if that's hitting the base station at neg 113, if that's an LTE base station, you got to get this thing shut off. If it's a CDMA base station, then it may not be so bad. Because you remember where the noise floors were for those base stations? Like I said, we're just about out of time, but I almost always do a path loss calculation just to make sure I don't spend time trying to shut down things that don't help, especially if they're hard, because sometimes it's hard to get these guys to shut stuff off. I don't know about you guys, but I've been told to get off property lines and, you know, blah, blah, blah. All right. Well, thank you for attending, and give us a holler if you have any questions. Have a great day.